So we are, and that's going to be, I think I'm going to change these two. Yeah, okay, it's fine. I mean, yes and no. So we're still on this problem. I'm just going to copy these, and I think I'm just going to rename this one to be just that, so we know it's that problem. We were step by step building in SymPy this group here, these. So now basically let's okay, so now we have a 3, and that's fine. So build these permutations. So these are permutations, and we're essentially let's go step by step. So P group construction, exactly. So we have these, and so we just the 3 group, right? A 3 group is essentially basically a group with order 9 specifically has a group with a field is a step by step. So combinatorics, the prime order 3 computes the group order as 3 squared. This specifies the construct 3 group of order 9. Okay. 2 permutations A and B are defined, each of order 3. The permutation being of order 3 means that if you apply the permutation 3 times, you to an element, then it's like applying the identity permutation, which means do nothing. So there's A, B, and then the identity permutation. Each permutation operates on 9 elements. A consists of 3 disjoint cycles. B also consists of 3 disjoint cycles. These permutations are chosen to generate a Heisenberg group, a non-abelian group of order 9. So creating the group, the commutator, so this is a commutator, generates the center. Okay, let's stop here for a second. The commutator generates the center. Let's go and dive into these. So I have a few blank screens in here, so let me see, are we doing, yeah, that's correct, okay, cool. So, yeah, I don't know if, I think we're recording, yeah, we're recording okay, it's all good. So I have a few fresh open grok windows to help me there. Okay, so what, in group theory, what is a commutator? Commutator, not communicator, commutator, yeah. Is in a group G with operation is defined as this measures the extent to which A and B fail to commute. In a group where the operation is written multiplicatively, the commutator is an element that, when multiplied by A and B, gives B and A. Specifically, if AB equals B and A, then okay. Okay, so how much they commute. Cool. Okay, if it's not E, then it tells you how far away they are from. It gives you a measure of how much not commute. Yeah. So the commutator generates the center. Permutation group. So what does it say? What does it mean that a commutator defines the center of a group. Remember the center. The center is, we checked this last time, the center is all the elements that, was it all the elements that commute with each other? No. What is the center of a group? Group theory. I think it was something like this, huh? Yeah, that they commute, exactly. The G equals GZ, exactly. So yes, okay, so a statement that a commutator defines is not accurate but likely first relation between commutators, commutator subgroup, and the center of a group forms A, B, yeah, exactly, for not commuting. So it measures how far A and B are from not commuting the identity element. So it's a group. Yeah, okay, it's all good. So we're using this commutator to define the center of the group. Why does a permutation group need that? So in SymPy, what is a permutation group? Object. With my group whose elements are permutations of a finite set. Okay. This part of SymPy's combinatorics module is to work with permutation groups, computational group theory. Okay, so permutation special functions on a set. Typically, the set function composition, for example. Yeah, okay, it's fine. SymPy, the permutation group. So of F, R, and D, create a permutation group. So what's the difference between creating a permutation group like this versus like this? Because here they are using the commutator. In the permutations used to generate the structure, there's no use in the context. Additionally, second example includes a commutator generates a center, which requires clarification. This is okay. Let's break down the. On a set of points, permutations F, R, D. Group G is the permutation group generated by F, R, and D. Yeah. Which models the group of all possible configurations achievable by applying sequences of these moves. Second example, simpler permutations. The group G is the permutation group generated by A and B, a subgroup of S9. The actual group depends on the relations between A and B. For example, A and B generate a group. Structural differences. Two generators, A and B. Yeah. That's the thing. Common in the commutator center. Your second cycle includes a common generates a center. This mistake and correct in general. So let's clarify. The commutator is a single element of the group, not a subgroup by itself. Does not generate the center. To check if in the center you compute. That's what I'm saying. So that's why I think it's odd. What's more, it just says 9. That's weird. G order. Like if you just do AB, shouldn't that actually give you 9? No, 8. Because it's 2 to the 3. No. It's AB. Permutation group. So that's currently a little confusing. I don't know what that would mean. And then something's not matching because it's why would it be order 9? So the file you generated states order should be 9, but SymPy says order is 8, and I don't understand why you're using commutator to create the permutation group G in the first place. Each permutation is order 3, since they consist of 3 cycles. The intention was to generate a Heisenberg group which has order 9, and is defined by 2 generators A and B, such that exactly the commutator AB has order 3 and generates the center. The group has order with the center of order 3. However, if SymPy computes the order G as 8, the group generated is not the Heisenberg group, but rather a group of order 8. It suggests 2 group instead of 3 group. Why the order is 8? To understand SymPy was 8. Let's examine the group generated. Let's use SymPy to explore these. Order of G. Oh, now it's okay. Now it's correct. Now it says 9. Order. Why does this output aid? This makes no sense. It's the same code, isn't it? A and B 036147258 permutation group A and B assert that the order is correct. Expected order. God. Yeah, okay. What? Oh, these, unless this is what? Unless this is 1? It's just done. No, this is weird. Print elements of the 3 elements of the group. In G elements. Okay, I think it's because of printing least G for G in think that's what's missing in the code. I know it's printing an 8 there. Yeah. Okay, now it makes sense. Now it's 9 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. Okay, never mind. That is correct. Never mind. It is correct now. Can you explain me why did you choose the commutator in order to create the parent group in the first place? Like what happens, the thing, it just might be a way to say like a shortcut, you know what I mean? Print. Can I just print? Oh god. Print AB. Okay, just printed that. The commutator was not used to creating the code. Instead, the group was created using the two permutations A and B as generators, and the comment about the commutator was included to highlight a key property that has been grouped. So maybe that was I mean, it includes all possible products of A and B. Oh, the inverses and the identity subject to is okay. So is this just a confusion around syntax? Around SymPy syntax and commutator syntax. Permutation syntax, okay. No, not that. Not that, so not that. I mean, what does SymPy? Yeah, okay, that's good, but like, what does it mean to? Like, why can I use these as a parameter value for the permutation constructor? That's what I don't understand. Well, you're just doing A and B here. Oh, so it's just passing it as that's what I mean. I think it's just passing it as an array. It's what if I just do these? It's the same, right? Then I understand. So what's in SymPy? What's the difference between a group created like this versus like that? think it's just a syntax thing, so maybe I equivalent. Okay. A single list, the permutation group constructor behavior simplifies expects an iterable, like a list of permutation objects as primary argument. When you pass A and B, it introduces a list of generators and creates a group. Okay. The arguments are treated as a tuple internally. Simplifies permutation is designed to handle this. Okay, so it's just a syntax thing. Fine. All right, that is good. So it kind of it already computes the thing by like calculating all the possible multiplications of these. So it's just these confuse me. These actually confuse me. This is a confusing comment. Okay, now next is modify the code so that it now make sure the group has a structure restricted by an exponent 1 plus 2. So basically a P group where P equals 3 and to the power of 1 plus 2. Whatever that means, right? That's what I'm trying to understand with that example. And then we'll still need to do the sub index plus, and then we'll at least have understood S, and then now we know the action stuff here, so we'll then work on the product, and then we'll try to define the operation by thinking about how do we induce the action. But now at least we've understood that. I don't know if that was the right order, but it's thinking quite a lot. So I'm thinking, do I give it a shot to a quick answer? Let's go. Let's see if it does well. Is the least common multiple of the orders of all its elements for a P group with exponent 1 plus 2? No, but it has a meaning, right? But wait, but writing, I think, but writing the exponent as 1 plus 2 has surely a meaning in group theory. Let's ask it to think hard. Yeah. Because now I just create something with like another permutation and that's it, right? And if I run these, it will likely say something else. Okay, there's a mistake definitely, but yeah, exactly. Y in addition. So essentially, what does this mean? This means the center ZG has order exactly. So the definition of an extra special P groups. An extra special P group is an non-abelian P group where the center has order exactly P. The derived subgroup has also order P. And the Frattini group, okay, whatever. The quotient is an elementary, okay, order breakdown. The total order is, so the one highlights the minimal size of the, okay, the one highlights the minimal size of the center. Order P, which is the defining feature, and the 2n emphasizes that the dimensions of the quotient is even. Okay, that is going to be complicated to understand. The one highlights the minimal size of the center. The size of the center. Okay, so let's focus on this one. So the first one tells you the size of the center. Let's focus on that one. So let's get the previous code back. With a simple 3 group. Let's work step by step. So that's what we had. Now ensure that the center has a mean size of 1. Yeah, well, that is actually easy, right? Because do we need to do anything? No. The center is always going to have like or is it that the size must exactly be 1? The minimal size of the center. No, order P. Okay, order P. Meaning it's the exponent. So order P. Stop. The group code to guarantee that the center has mean order of 3. But I mean that is kind of guaranteed, right? Because A and B have order 3. So maybe there's nothing that needs to be done there. I don't know. I'll stop here. I'll stop here. I'll go back to it later. So we need to basically modify this this way. Cool. See you in the next session.